we would like to talk about how buffer tank work and the sizing. Okay, moving on to the next slide. So what we'll include for this lecture will be how does buffer tank work? Number two, how to size a buffer tank. And then number three, why use buffer tank? That's a recap for that. Let's moving on to the next slide. So how buffer tank work? Question. So as you can see at the photo on the top left, a buffer tank act as a thermal energy battery for heating hot water or chill water system. They lack enough water volume during the low load condition. So they can be used for geothermal uh, heat pumps or chill water system or the low mass boilers, and we will show you how they work with some examples and how to calculate the size. And we will show you two examples here, and then one for the chill water systems. You can see the blue one at the second left, and then the other will be heating hot water. So let's move on to the next. So let's talk about how does a buffer tank work and show answers to prevent the cycling. A buffer tank, so basically it's an insulated storage tank, so that adds additional mass to absorb the heat, absorb or reject the heat during the low load conditions. So also buffer tank serves several important functions. A buffer tank prevents the short cycling of the boilers, heat sources, and the chill water systems. So normally short cycling occurs when the heating or cooling system turn on and off rapidly, like turn on for 1 second and then shut it off the next second. It's not that extreme, just as a quick example for you guys. And due to the small fluctuation in demand, so this can be inefficient and cause wear and tear on the heating and cooling equipment. Is one of the top cause of the failure in the heating system. So imagine you have a car and then you started the car, start the engine, and you shut it off the next second, and then you start it again and shut it off. Then will be the cyclic repeating motions that will cause a wear and tear of your engines for sure. And the buffer tank provides a reservoir of the heated waters, allowing the system to operate more steadily. So a buffer tank can help prevent a compressor short cycling during the low load in a geothermal or chill water systems. Okay, so that's a good advantage for the buffer tank we can know now. So moving on to the next slide. So how to size a buffer tanks? So here are two different formulas, one for the chill water system and another for the geothermal heat pump system. So moving on to next. So 2.1, let's moving on to this slide. It's a chill water buffer tank sizing. And the following formula is offered by one manufacturer of the buffer tank. And any calculation you make, it should be confirmed by the mechanical engineer or the manufacturers. So you can see at the left photo for the formulas, volume of the buffer tank equals to C times VR minus VA. So where C equals chiller capacity in tons and VA equals to actual chill water volume in gallons, and then VR equals to the recommended system volumes per ton as recommended by chiller manufacturers, and you will need to make up some value for this in order for you can plug in the numbers. So now you can see on the right s- side of the photo for the formulas. So let's say, okay, let's put some number here. We have a smaller chiller of the 100 tons, and the manufacturer requires 6 gallon per ton minimum volumes. And if we use this information, we can drive the value at which anything below the value will require buffer tank. So that's a threshold we are looking for. So let's do a quick calculation here. So 100 tons times 6 gallon slash tons equals to 600 gallon minimum system volumes. If the actual system value is less than 600 gallons, then a buffer tank will become required. So let's say our system volume is 480, so which is less than 600 gallons. So by using the lab formulas, chill water buffer tank calculations, chill buffer tank volume will be equals to 100 tons times 6 gallon per ton minus 480 gallon. So which will give you the difference, which is 120 gallon buffer tank volumes. So from the calculation, you can see that for every gallon, the existing system total is under 600 gallons. Another gallon will be added to the tank capacity to provide the minimum required of the 600 gallon of the system volumes. So that's how it works for the chill water systems. So let's moving on to the next one. 2.2. This is a water source heat pump buffer tank sizing. So the following formula is in a very similar fashions. So it's offered by one manufacturer of the buffer tanks, and any calculation you make should be confirmed by the mechanical engineer or the manufacturers. So the calculation is meant to allow for the boilers or source of the heat to run for a minimum amount of the time before cycling off. So you can see at the left photos for formulas, V equals M times QH minus QM divided by T times 500. So where V equals to buffer tank volume in gallons, M equals to desired heat source minimum runtime or the on-cycle time, which is in minutes, and then QH equals to a heat source output minimum BTU per hour, and QM equals to heat output for minimum system load, which is also equals to BTU per hour, and T equals to the temperature rise, so delta between the supply and the return degree Fahrenheit. So 500 equals to 8.333 uh, pound per gallon weight of the water times 15 minutes per hour. Okay, so now let's plug in some numbers. So for these examples, you can see on the right side of the photos, let's assume we have the heat pump LED output at minimum of 60,000 BTU per hour, and that manufacturer recommend a minimum cycle time of 10 minutes. And that smallest zone is 9,000 BTU per hour, and the smallest zone is 9,000 BTU per hour, and the radiant heating zone allowable temperature differentials is from 90 to 100 Fahrenheit. So if zone 1 to 3 were off, only zone 4 was running at 9,000 BTU per hour, our calculation will be like this. So finally, let's get to the calculation now. So now we can do the buffer tank calculations. V equals to 10 minutes times 60,000 minus 9,000 divided by 100 minus 90 times 50, which will give us the final number now, 102 gallons. From the calculation, we can see this for 102 gallons is a buffer tank capacity to provide the minimum required of the system volumes. That's good now. Okay. So now we're running through all the calculations. So that's a quick recap here. So for why use buffer tank? What's the reason to use it? So here's what happened during the low load conditions. The boiler and the compressors turn on and quickly satisfy the demand and shut it off just as quickly because of the low load condition. Maybe shut it off maybe in 10 seconds, 5 minutes, and then turn it on and shut it off in one cycle in 5 minutes, and it will restart in another 5 minutes. So that's not doing very good for your compressors or your boilers. So this short cycling of the on and off continuous under the low load conditions, creating the additional wear on the boilers and compressors. So by adding this additional load and water volume with the buffer thing, this short cycling period is reduced or eliminated during the low load period. So a buffer tank basically is a insulated storage tank that add additional mass to absorb or reject the heat during the low load conditions. So low load conditions add a buffer tank. So that's pretty much cover for this lecture, and thank you for your time, and would like to see you in the next one. Thank you and bye.